Hello, peoples. This video is specifically intended for the AP class because College Board and AP love to define open and closed systems. So their definition, as you can see here, and obviously feel free to pause the video if you need to, but their definition of an open system is when external forces act on the system to do work to change the energy of the system. Now, a system is just, as you'll see as we do these examples, just what objects you're defining as part of a system. It's not a big deal. And a closed system is where there are no external forces doing work to change the energy of the system. You could use the phrase that all forces are internal to the system. So that's a difference. In an open system, if there's an external force acting on the system to change the energy, it's called open. If there are no external forces acting on the system to change the energy of the system, then it's closed. Simple as that. So let's do that here. This is the handout that you got in class, and it goes through each of these examples. So let's just get used to this. And this happens usually multiple choice AP people that, they'll just say, like, is the system open or closed? Under what conditions would it be opened or closed, or something like that. Sorry if you hear all this. This is my cat who will not leave me alone while I try to make this video. And I'm not editing that out because, no, I'm not editing that out. Anyway, so let's take this first example. You got a planet orbiting the star. If we define the system as only the planet, are there external forces acting on the system? Yeah, it's called the gravity of the star pulling on that planet. So if you just look at only the planet here, are there any forces acting on the planet? Yeah, the star. So this is open because star applies a force. It's an external force acting on the system. If the system happens to be the planet and the star, are there any forces outside of the planet and the star acting on the system? The answer is no, so this is considered a closed system. No external forces, or all forces are internal to the system. And finally, if it's just the star, that is an open system, because this planet also exerts gravity on the star. So it's an open system. Planet applies a force. Why did I spell force wrong over there? Planet, and now I did this wrong. Planet applies force. That's it. I mean, you just have to define the system. All right, in this example here with the block on a spring, okay, there's a mass and it's going to oscillate, whatever. And you have to determine if it's open or closed. It does say negligible friction, thank goodness. So if it's only the block, are there forces acting on the block that are outside the block? Yeah, this is open. You've got the spring acting on the system and the force of gravity. You got both of them acting on the system. If it's just spring and earth, okay, so now we're just talking about the spring and our planet. Yeah, this is an open system. You know how I know? The mass is applying a force on the spring. Granted, the Earth's gravitational pull will pull on the spring, pull on the mass, which compresses the spring, but in the end, the mass is applying that force on the spring. If it's only the block in the spring, that is also open because Fg acts on that system, the force of gravity. So if you take into account the mass, the spring, and our planet, which I just drew there as a weird circle, that is a closed system. Since all forces are internal to the system, or there are no external forces acting on the system. It's that simple. All right, normally, like in class, when it says, give an example of an open system. So you've got this, an object, and it's being dropped above the surface of our planet. Okay. Example of an open system. So the reason this thing falls is because Earth is like, hey, you're attractive. Why don't you come down here? That doesn't sound creepy at all. But there is a gravitational force that pulls that mass down. That's why it will fall. So an example of an open system We could do, for A, we could do the object is an open system, because only if you just circle the object, well, then Earth's mass is going to apply an external force on it. So I'll just write Fg applies force. Another example of an open system is Earth. Since force of gravity caused by that little object applies a force on Earth. I know it's small, but it does. It's true. And if you want, that's it. If you want to do an open system, or excuse me, a closed system, oh my goodness. If you want to do closed, then it's both object and the Earth. Object and Earth. And the reason is there are no forces outside of object and Earth acting on the system. Let's assume no air resistance, please. Okay. So you've got object and Earth together. All forces are internal to that system. Let's assume no air resistance. If there was air resistance, then we'd have to include air resistance in the system, or air in the system, to make it a fully closed system. Right, another example. If my computer will allow me to scroll here, but it's being cranky pants. Somebody put on their cranky pants today. Seriously, where'd it go? Okay, enough of that. I don't know why it's being like that. A block sliding down a rough surface. Now, this rough surface phrasing is directly from AP, and you know that that means you must include friction. So, is it open or closed? So, let's just draw this out. You've got a block sliding down, and there is friction. So, I'm just putting mu is there. If it's only the block, you should be able to answer this by now. You shouldn't need me to talk your way through this. Basically, are there any external forces acting on the block? If there are, it's an open system, because both Fg and Ff act on the system. Okay. If you do the block Earth system, are there any forces or any external forces acting on the block Earth system, excuse me? And the answer is yes, there's still friction, so it's an open system. C, it's everything. It's the block, it's the incline, and it is the Earth. So are there any forces outside of those three things acting on the system? The answer is no, so that is a closed system. One thing to take note of here, because you say all forces are internal to the system, but in terms of energy, friction is, supposedly doing negative work to change the energy of the system. But if friction is part of the system, then that energy must remain within the system. So you may want to pay attention to the phrase friction causes a change in internal, you can use the word internal, or you can use thermal energy of the system. So they like that phrase, because they may ask, where did that energy go? If you start with all this potential and you end with less kinetic, what happened to that energy? You could say friction did negative work, or you could say friction caused a change in temperature of our system, or a change in thermal or internal energy. I mean, those are all phrases you should know. But if you rub your hands together, they get warm because of friction. Well, same thing here. When something slides, some of that energy is dissipated as heat, so is a thermal energy. And that's basically it. That's how you define systems. Nothing really else to it. Is it open or closed? Are there external forces acting on the system or not, as you've defined the system, of course. Now, this is where it gets a little weird. Okay. Come on, scroll down. Where'd it go? Where'd it go? I'm really not happy with my computer right now. Okay. No, we were just there. I'm so sorry about this, people. Maybe I should edit this out, but it's not scrolling for me. Oh, there we are. Okay. So let's look at this. A basic block sliding down an incline, and of course there's friction. Why did I not put friction? Let's put some friction in here. All right, the old way, okay, what just happened to my mu? It disappeared somewhere, and I want it back. The old way of doing this, or the way that you're going to do most often, is the work energy theorem, right? You write out kinetic energy initial, AP, kinetic energy initial plus potential initial plus work equals K final plus UG final. Okay. Not moving in the beginning. Above height 0, yes. Work done by friction, yes. Kinetic energy in the end, it's moving, yes. And potential energy in, no. So I'm just going to do a little math here. We have mgh, which is d sine theta, right? Minus the work done by friction, which would be mu, times the normal, which would be mg cosine theta on an incline. Don't lose the distance. And that's going to have a final result of 1/2 mv squared. And yeah, the math divides out. That's not really relevant right now. But that's the way we did it before. Now, I don't know why. I'm sure there's a reason. But there's something known as the work kinetic energy theorem. And it's often said this way. Kinetic energy theorem. And in this scenario, you simply write out kinetic energy initial plus work equals kinetic energy final. And in this scenario, the gravity does do work. Does work. Because it's not a form of energy. Our system is really more focused on just the block. Everything we've done so far has been block Earth system. That's why it's an internal force. It can't do work. That's why it's a form of energy. Now we have Earth as not part of the system, and it can do work. So here's how, check, this is the weird thing. I'm going to just draw a quick FBD here so you can see it. Here's our block sliding down the incline. We've got normal. We've got FGY, we've got FGX, and we've got friction. I don't know why there's a plus sign there. I don't even know what that is. And this system will accelerate or travel a distance d, right? Okay. This is where it gets funky. We still, is it moving in the beginning? No. Is it moving in the end? Yes. Are there forces doing work? Yes. Friction. There's the work done by friction, but then there's also the work done by the force of gravity. I don't know why I wrote that like that. That should be W, force of gravity. Okay. I want you to see this. I should have done this in a different order, so I'm gonna do this one first. The force of gravity is mg. Okay. Well, excuse me. The force of gravity that's doing work, it's not FGY because FGY is perpendicular to the direction of motion, so it's not doing any work. FG parallel is doing work on the system over a distance d. And FG parallel is mg sine theta, right? And that acts for a distance d. It's cosine 0 because they're both in the same direction, so I'm not even writing cosine 0. It's just, that's what it is. Then you've got the work done by friction, which is negative mu times the normal, which is mg cosine theta. Don't lose the distance. And then afterwards, it's moving, 1/2 mv squared. Now, check this out. This is why I don't get it, but this and this are the same exact equation. The whole point is you can either say work is a form of energy, gravity is a form of energy, okay, which is just mgh, or you say that gravity does work and applies a force of FGX, which is mg sine theta, over a distance. In the end, you get the same thing. It just depends on how you define the system. Personally, I think it's just so much easier to include gravity as part, or the Earth as part of the system, so you get gravitational potential energy. But I just want you to be aware that you might be asked to use the work kinetic energy theorem, and in that case, gravity does work because the Earth is not part of the system. So that's about it for this video. It's just defining systems. I mean, there's no recap here. It's just open or closed. Open, external forces do work to change the energy. Closed, there are no external forces to change the energy. And the problem that we did as an example took the gravitational potential and energy out of the work energy theorem, and it became the work kinetic energy theorem, where gravity does work. And in the end, you still get the same equation. So it's a little odd. But anyway, I hope this video helped with systems. Know that AP will most of the time use this as multiple choice questions, defining open and closed systems. And that's about it. So, there might be a couple things I would change about this video, but I'd still give it 3 out of 5 stars. Thanks for listening.